Hello viewers and welcome to Pop Proof's Advanced Physics channel. In this channel we are going to have a rigorous proof of Kepler's three laws. We are starting with the first law, which says that planets revolve around the sun in an elliptical orbit with the sun at one focus. I'll just write it as elliptical orbit. Now an ellipse is part of a conic section. The conic sections include parabola, circle, hyperbola, and of course ellipse. Now every ellipse or elliptical orbit has two major axes or two axes. The principal one is the longer one and the minor one is a shorter one. If you divide the principal axis into two, so this is the center of an ellipse, the distance from one point here to the center is called the semi-major axis. And the distance from this to the center is called the semi-minor axis. There are two foci, you could also say foci if you want, of an ellipse, and the sun happens to be at one focus with the planet revolving around it, like so. Now, when the planet is closest to the sun, we call that position apoapse. And if the planet happens to be farthest from the sun here, we call that position periapse. If it is the earth, we call it perigee and apogee. If it is the sun, we call it apohelion and perihelion. Helion means sun. G or geo means earth. Well, one focus is displaced from the center of the ellipse by a factor of E. So if you multiply A by E, a factor for which the sun is displaced from the center of the ellipse, you get this distance. If E is equal to 0, this conic section will be a circle. That means the sun will be at the center, and that will be a circle. If E is equal to 1, that means the sun is located here, and we call it a parabola. If E is greater than 1, that means the sun would have been outside the ellipse, and we call that a hyperbola. So E is called the eccentricity of the ellipse, and that defines the conic section. So at the periapse, the distance from the focus at which the sun is located will be A plus AE. So the distance from the sun to the periapse will be this distance A plus AE, which is equal to the semi-major axis 1 plus the eccentricity. That is, if you factorize the semi-major axis out. And the apoapse, the distance from the sun to the apoapse would rather be, so the whole distance from the center to the apoapse is A, and this is AE. So that will be A minus AE, and that will be A into bracket 1 minus the eccentricity. We are doing this because it's going to help us prove the first law rigorously. We need to know certain things about the ellipse before we start proving that. Now let's get into it. Now the rigorous proof is such that, now let's remember this universal law of gravitation that Newton discovered, that the force of gravity in vector form is equal to negative the gravitational constant times the product of the two masses divided by the magnitude of the distance between the two objects squared in the direction r roof. This is a universal law, and you can't prove this. You can't, because it was not based on first principle. This is a law, and the law is not meant to be deduced. However, you can prove certain things, like how we got the capital G. The value of capital G is approximately 6.7 times 10 to the power negative 11. And the unit will be Newton meter squared divided by kilogram squared. That is the approximate value of G. And this was experimentally determined by Henry Cavendish, who happened to be a British, through his experiment that he conducted. And you can also infer that the force of gravity is an inverse square law based on experiment using telescopes and calculating distances between the Earth and the Moon and the acceleration of, say, an apple on Earth. You can link that to infer or to conclude that in fact this is an inverse square law. So given that this is a universal law of gravity as discovered by Isaac Newton, we are basing on that to prove the three Kepler's laws, starting with the first one, which says elliptical orbit. To prove that, let's pick two masses. Let's call this M1, then call this M2. Separated by a unit vector, a position vector r, and with a unit vector pointing in that same direction. Then let's pick an origin, an arbitrary origin. Let's call this origin O. The unit vector, the position vector of M1 from the origin, let's call that R1. And the position vector of M2 from the origin, let's call that R2. So the vector R is equal to R2 minus R1. These are how vectors are added. That if you have a net vector pointed in this direction, now it is going to be the summation of these two vectors. But already R2 is pointed in the direction of R, so that will be positive, but R1 is pointed to the tail of R, so we need to reverse that vector. That's why we have this negative sign, minus R1. And then again, the next thing we can write is that the gravitational force on object 2 is going to be equal to, in vector form, of course, it's going to be equal to the universal constant, product of the two masses, divided by r squared in the direction r roof. But it is an attractive force which will point opposite to the unit vector r. Called M1 is attracting M2. So there will be a negative sign here. Now, the force of gravity on object 1, is going to be the same gravitational constant, M1, M2, divided by r squared in the direction r roof. And that force will be pointed in this direction. Now M2 is now attracting M1 in this direction. So if M1 would move, it will move in the direction of our roof. So there is no negative sign here. Now, based on this vector addition and the gravitational forces on each of the objects, we are going to prove Kepler's first law. Kindly subscribe, click on the notification bell, share, comment, and like my videos. So you pick an origin. There are two masses, M1, M2. The unit vector going from M1 to M2 is R. The unit vector from the origin to M1 is R1. The unit vector from origin to M2 is R2. And we established this equation that the unit vector, the position vector R, not unit vector, is equal to R2 minus R1. Then we also established that the force of gravity on object 2 is equal to negative G, the product of the masses, divided by r squared in the direction r roof, given that r roof is a unit vector pointed in the direction of r itself. The force of gravity on object 1 is equal to capital G m1 m2 divided by r squared in the direction r, but that is going to be positive, it will be pointing in the same direction as r, unlike f2, which will be pointed backward. Now let's see the acceleration of object 2. Given that the force of gravity on object 2 is this, the acceleration on object 2, so this implies that the mass of object 2 times the acceleration of 2 will be equal to negative g m1 m2 divided by r squared in the direction r roof. So if you would want to find acceleration of object 2, a2, which is a vector now, it is going to be equal to, now the m2's cancel out, then you have negative g m1 divided by r squared r roof. This is really important. Now we are going to write the acceleration of object 2 as the second derivative of the position function or the position vector. The second derivative of a position vector gives you acceleration vector. So the position of m2 is r2, and that will imply that the second derivative, the squared r2 dt squared, is equal to negative g m1 divided by r squared in the direction r roof. So similarly, for f1, this will imply that m1 times a1, which is a vector, is equal to capital G m1 m2 in the direction r roof divided by capital R squared. Also implying that, let me unbox this, which is going to help us in our subsequent calculation. This will imply that a1 m1 would cancel, is equal to capital G m2 in the direction r roof divided by r squared. And if we write a1 in terms of its position from the origin, m1 is located a position vector r1 from the origin, so the second derivative of r1 would give us a1. So the squared r1, which is a vector, dt squared, is equal to capital G m2 in the direction r roof divided by r squared. And this is also to be unboxed. So this equation 1 and 2 are going to build the framework on which we are to prove Kepler's first law. Now, as we can see from the first vector equation that we wrote, r is equal to r2 minus r1. And now what we can write from that is that if we take derivatives of this vector equation, let me do that here. Given this equation, we can take second derivative and say that the second derivative of the vector r dt squared would be equal to the second derivative of r2 dt squared. We are taking the derivative with respect to time minus the second derivative of r1 with respect to time. We wrote this equation based on the first premise. But then we know the square r2 dt squared, which is this equation. And then again, we know the square r1 dt squared, which is this unboxed equation. So then we can write that the second derivative of the position vector going from the object 1, the mass 1 to mass 2, with respect to time squared, would be equal to, now we know this quantity, we write that as negative g m1 divided by capital R squared in the direction r roof minus Then we have the square r1 dt squared, which is also g m2 r roof over r squared. So we have capital G m2 divided by r squared in the direction r roof. Pretty much important. So we have the squared r, the t squared is equal to, factorizing negative g over r squared, common to both quantities. Then we have the summation of the two masses. To denote that better, that is equal to negative g into bracket m1 plus m2 divided by capital R squared in the direction R roof, which I nearly forgot. Oops. So we have the squared R, the t squared, plus capital G, the summation of the two masses, divided by capital R squared in the direction R roof equals 0. If you bring the whole of this quantity to the left, this is a differential equation we are to solve. So if we are to prove Kepler's first law, we need to solve this differential equation. The square r, the t squared plus g m1 plus m2 r roof divided by r squared is equal to 0. It is a Herculean task, but we give it a try. And we are going to prove it. So the differential equation to solve to prove Kepler's first law is that the second derivative of the position function between the two masses plus the gravitational constant times the summation of the two masses r squared in the direction r roof is equal to 0. Now, given this differential equation, we need to get rid of the vector r. It is difficult to deal with vectors. And to do that, we are going to be mathematically smart by taking the cross product of the whole equation. To take the cross product, let's pick the position vector r and cross it with the whole equation here. The squared r, the t squared, plus capital G m1 plus m2 divided by r squared in the direction r roof, and that giving us 0. So the cross product is a tool that we can mathematically use to proceed with our proof of the elliptical orbit. Now r cross the whole of this quantity is going to be r cross this cross the squared r, the t squared, that's the first of the quantities, plus g m1 plus m2 divided by r squared. Then the vector r cross the unit vector r. That's how we do the cross product. You cross vectors, you don't cross scalars. So the whole of this is a scalar, so you cross r and the unit vector r, and that gives us 0. Also good. With this vector equation, r cross the square r dt squared plus the whole of this scalar r cross r roof equals 0. We can split the equation and say that r cross the squared r dt squared is equal to 0. That is the first part. And then again, the whole of this is equal to 0. Because if you have a vector r it is in the same direction as the unit vector r roof. If you cross a vector by its unit vector, which are both pointed in the same direction, that will be 0. Because cross product says that you multiply the magnitude of the two. The magnitude of this is capital R. The magnitude of this is 1, so times 1. Times the sine of the angle between them. The angle between them is 0, and then sine of 0 is equal to 0. So the whole of this is 0. So we're going to focus on this equation. Now, the vector r cross its second derivative is equal to 0 would mean that the time derivative, that is d dt, of the vector r cross its first derivative, dr dt, is equal to 0. So the implication of this equation is that the time derivative of this quantity is equal to 0. And in fact, if you take the derivative of this cross product, you get back this. So that is to say, this quantity is a constant. And we can name it. We can give it a name. Let's call r cross dr dt, which is a constant in the revolution of the planet. So let's give it another name, h, which is a vector 2, is equal to the position vector r cross its first derivative, dr dt. So this implies that if you have the vector r and then you have the vector dr dt, if you take the cross product of the two vectors, you produce vector h. And cross product means that that vector h is perpendicular to both of them. So if this is vector h, it is perpendicular to r, at the same time perpendicular to dr dt. That is what we mean by cross product. And if h is constant throughout the whole of the revolution of the planet or any mass around another one, that will mean that the motion of that object now is confined in the 2D plane. It is confined in the 2D plane because the cross product of this and that will give you a vector h, which is a constant, lying in the third dimension. It is a line in the third dimension because it is perpendicular to both r and then the r dt. The only way h could be a constant pointed in the third dimension is that r and the r dt are lying in two-dimensional plane. So if these two are the two vectors which are crossed, then h will be the 3D, the third dimension pointed upwards, whereas r and the r dt are lying in two-dimensional plane. We are going to continue this in the next episode. Watch out for the next episode as we end the proof of Kepler's first law. Now we have reached the part where we have got a constant vector in the revolution of the planet around the sun. That constant vector is h, which is defined as the cross product of the position vector r and the r dt. Stay tuned.